All right, today's notes are going to be on circuits. So we've talked about magnetism, we've talked about current, we've talked about voltage, that potential difference that's going to make your electrons move. So now we're basically going to put it together into circuits, which generally tends to be something that all of y'all really like to do. So the first thing is the basics. You've already built some circuits last time. Last unit you used the batteries, the wires, and the resistors to make your circuit. Now what we're going to do is basically we're going to be replacing those resistors with your light bulb. So your light bulb's actually going to be like your resistor. It's going to slow down the current as it allows it to take that power to produce that light. When we talked about power ratings of light bulbs, so with your power rating of your light bulb, you're looking at how fast that moving energy is converted into light energy to light your light bulb. So what we have to do first is we have to come up with a way to draw all this stuff. So the circuits that you see over here on this side, those are what you normally look at. You have your battery, your positive, your negative, and then you have your light bulb. What we have to do is we create something called a schematic design. And with your schematic design, what you do is you're basically drawing it in a more uniform manner, so that way everyone, no matter where they're at, all of your schematic designs can be interpreted so everyone knows what your circuits. So here you have your battery represented by the two lines, a longer line and a shorter line. The longer line represents the positive, the shorter line represents negative. Then all of these lines in the middle that are all nice and straight, those are your wires. And then you over here on this side, you have a light bulb. So you're going to need to memorize all of these different symbols. So make sure you draw these in your notes. So on the left, you have your wire. Your wire, you'll notice, is straight lines. Wires are always going to be drawn as just nice straight lines. We don't overlap them. We don't crisscross them. We generally don't draw them in circles. We always draw them, no matter what picture we're looking at, we make them into nice straight lines, 90-degree angles. In the next one down, you have your resistor. So your resistor slows down that current. And so we draw it and we make these little like up and down, almost like mountains in the middle of it to be your resistor. The next one is your light bulb. Your light bulb is a type of resistor since it's going to slow down your current. So we draw it with a resistor and then we draw a light and a circle around it to symbolize that it's a light bulb. All light bulbs are drawn the same no matter what size they are. The next one below that is your plug. Okay, your plug is a circle around it with two lines, similar to your battery, indicating that the longer line is going to be your positive terminal and the shorter line is going to be your negative. Your battery over here is very, very similar. The lines coming off of it just show the wires that would be connecting to your circuit. Again, your positive and negative. You do not have to draw the positive and negative on your battery when you actually draw your schematic designs, but it is going to be important for you to know which way the current's moving. Next one down you have are your two different switches. So these are going to allow you to turn on lights, turn off lights. If your circuit is considered to be open, an open switch, that means that there's a break in the circuit. So you have two little switch dots on the side. That's going to show you where your switch is at. And then since it opens, you'll notice that there's a break, so the electrons aren't able to flow, so your lights are off. So an open switch, lights are off. If you close the switch, that means that you continue the circuit. Now there's a nice even path for the electrons to flow. And so your closed switch is going to be when your lights are on. All of the electrons can travel. And then the last one is going to be your capacitor. Your capacitor, you'll notice, is two parallel lines. One's going to be positive, one's going to be negative, just very similar to your battery. But the difference is that the capacitor, as we've talked about before, is made up of two parallel plates. So you have two parallel lines because your capacitor is two parallel plates. And again, then you just have like the wires coming off of them like you did on the switches, the battery, the resistor, and the light bulb. Okay, so you're going to want to memorize this chart. You're going to have to practice drawing these, and you'll get a lot of that throughout this unit with our homework. Okay, so with your circuits, kind of talked about this already. Your open circuit is an open switch in which your current doesn't flow. So this means that your lights are going to be off. Okay, you're literally preventing the electrons to go from one point to another. Electrons are not able to jump across the switch, so they're just going to stay in that spot. They're going to move right up to they get to the switch, and then that's it. They can't go any further. Your closed switch, or closed circuit, is once you've closed that switch and now the electrons are able to move, you've completed the path, and so they can sit there and continue to travel on as they go from, in conventional current method, from positive to negative. Okay, so your current flows. Closed switch means the lights are on. Okay, the next one is your short circuits, and these somehow you've overloaded the circuit. Your short circuits are very, very dangerous. They can cause fires. With you guys, when we're doing the labs, if you make a short circuit, you'll blow out the light bulbs. Okay, or if you run a circuit that doesn't have any resistors in it, and you're just connecting the wire from positive side to the negative side of the battery, you'll notice that it'll get really, really, really hot. And so that can be when things start to break, okay, potentially causing fires in your house. All right, the next thing we have to look at is our battery. Our battery, we come up with a term called EMF, which is represented by this cursive letter E. Okay, and really what your EMF is telling you is it's just telling you your terminal voltage. So the voltage at a specific side of your terminal. So you have your positive terminal, negative terminal. Terminal voltage is looking at it just on that one side of it. All right, so your first type of circuit is going to be your series circuit. So your series circuit, what you'll notice is that we have multiple light bulbs. So in your home, your classroom, you look up, there's all these different lights connected. Okay, and so we try and figure out how are they? Are they series or are they in parallel? So a series circuit, what you'll notice is you have one light, then another, okay, and then another. And then it connects back to the battery. So here we're drawing current, where the current is drawn on this one. It's actually going in the direction that it actually flows, not conventional current. Okay, so it's going from negative back to the positive. And so your current is going to go through every single one of these light bulbs. Okay, the best example of a series circuit are Christmas lights. Okay, you have them, current goes from one to another, to another, to another. So then on the right, here's a picture of what it would look like drawn in a schematic design. So going from conventional current method, the current would start over here on the positive side, and it goes through one light bulb, another light bulb, another light bulb, using up all that energy until it gets back, and that when it reaches back to the negative terminal, it's again at, has 0 volts, or 0 potential. Okay. If you wanted to take a series circuit and you were to calculate your total resistance, we come up with this term called REQ. REQ is what total resistance is. So instead of saying that we have those 3 light bulbs, what would happen if I combine them into one big light bulb? Okay, or instead of on a Christmas light strain, instead of having 50, okay, how much would it be if I had 1? To do that, you just end up with your equation R1 plus R2 plus R3. That's going to be your resistance measured in ohms for each one of your separate resistors. So you just literally add them up straight as it is. So if you look at your schematic picture, you go from 1, 2 to 3. Now you have one resistor put together. Okay, with your resistors, the current is going to be the same everywhere. Okay, because in order to go through one resistor, you have to go through the second resistor, you have to go through the third resistor. So your current is the same everywhere in a series circuit. Okay, your potential will be different. So each resistor is going to take some of that potential, so that way when the electrons get to the next one, they'll have less potential. When they get to the third one, they'll have even less potential. So for a series circuit, current is the same, potential is different. Okay, so if you look at number 1 on the homework problem, okay, you have 4 different resistors. Each resistor is identical to each other in 15 ohms. You need to draw these out for every single problem that you work through. Always draw your schematic design. So you have your potential of 45 volts, and then you have all of your resistors. So first thing you need to do is find out REQ. To find R equivalent, you're going to add up all of your resistors. That REQ equation that was on the previous slide is just generic R1, R2, R3. It can go up to as many as you have. So if you have 100 Christmas lights, then it would be 1 plus 2 plus 3 all the way plus 100. Okay, so here we do 1 plus 2 plus 3 plus 4. They're all the same. 15, 15, 15, 15 gives you 60 ohms. That's your total resistance. Then, in order to calculate your current through the whole circuit, okay, anytime you're looking for the current in a series circuit, you always want to use the total resistance. So you're going to do 45, your volts, rearrange Ohm's law, divided by your current, and you get 45 divided by 60, which is 0.75 amps. That is your total current going through the whole circuit, and would be the same for the current going through every single one of those resistors. All right, your other one is going to be your parallel circuit. What you'll notice with the parallel circuit is we call this the branch one. And so basically the current has an option. It's not going to travel through all 3 light bulbs. It's only going to travel through whatever's on its path. So you'll notice that as the current travels down, again, we're going in the direction that the electrons flow, okay, not that conventional current. They're going to come down and they're going to meet this point in the wire. When they meet this point in the wire, they have a choice. They can either go through this light bulb or they can keep on going. If they go through this light bulb, then it's going to pass through it and it's going to go back into the battery, towards the battery. Okay, it's done. It never sees the other 2. If it continues to go straight, then they have the option at the next break. They can either go through that light bulb, again back to the battery, or it can continue on. And then at the end, it has no other option, so it has to go through the 3rd light bulb. So literally you're splitting the current into 3 different directions. Okay, and the current is only going to flow through one path. Okay, they don't get to go back through a 2nd light bulb. Okay, so then when you draw it, okay, your schematic design, same thing. You have all these different branches. Each light bulb is on its own wire. They are completely separate from one another. In your parallel circuit, if one light goes out, the electrons will just flow through the other one, so all your lights will stay on, whereas in a series circuit, if one goes out, it breaks it right there. You've created an open circuit and your current no longer can flow. Okay, now to find your total resistance, or your R equivalent, in a parallel circuit, it's a little bit different. The equation is 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3. So really you're going to be taking your value x to the negative power, negative first power. So with all of your answers, you're always going to make sure you invert it at the end. The other thing is pay attention to how you add fractions. 1/3 plus 1/3 plus 1/3 is not 3/9. Okay, so pay attention to your fractions. If you don't like fractions, you don't want to deal with them fractions, put it in decimal format. That is perfectly fine. Okay, so again, all you're looking at for REQ is instead of having 3 separate paths, what would it be like if I only had 1? So if you look at number 8 in your homework, you have 3 resistors. Each resistor has their own resistance value, 60, 30, 20. So if I want to figure out what REQ is, I'm going to add it. 1 over R1 plus 1 over R2 plus 1 over R3. So 1 over 60 plus 1 over 30 plus 1 over 20. Add that up, and then you're going to inverse it, x to the negative 1 on your calculator. And you get, so your answer will be 0.1. Then when you do x to the negative 1, it becomes 10 ohms for your REQ. Okay, with your parallel circuits, your voltage is the same at each one. Since it's each almost like its own separate circuit independent of the other ones, your potential will be the same for every resistor in a parallel circuit. Your current, however, will be different because current is going to be based on the resistance. Since each one is separate, the current through every path is going to be completely different. So the first thing I'm going to do is I'm going to calculate my total current for my entire circuit using Ohm's law again. So it's going to be I equals V over R. So 90 divided by 10 gives me 9 amps. Then I'm going to go back and I'm going to figure out the individual current for each circuit, for each part. So I'm literally treating each one as their own circuit. So for the first one, I have a potential of 90, and then it's connected to a 60 ohm resistor. That's it. The other 2 paths are irrelevant. So I'm going to do 90 over 60, gives you 1.5. Do the same thing for the 30 ohm resistor. Again, it's its own separate circuit. It's like the other 2 don't exist, so it's 90 divided by 30, gives you 3 amps. And then for the last one, it's 90 over 20, which would give you 4.5. So you'll see that you end up with completely separate values for every single one of them. Okay, so here's a big summary for you to see. Here's your series circuit versus parallel. Same wire, different wires. For your current, your total current in your series circuit is equal to your current at every point. It's going to be the same because you have to go through everything else. So your I total equals I1, which equals I2. For a parallel circuit, if you find the total current for the whole circuit, you can add up all the individual pieces and it'll end up being your total. Okay, then for your potential difference, the two topics basically switch. So your potential difference in your series circuit, the total for the whole circuit is going to be equal to the one voltage going through 1 plus the voltage going through 2. Again, as it goes through the light bulb, you're losing potential. As you go through the next light bulb, it's losing potential. So if you add up all the potential that each one uses, you'll get the total potential for the circuit. Parallel, since they're each like their own separate circuits, your voltage of your battery is going to be equal to your voltage through the first resistor and through the second one. And then you have your two resistance equations. Req equals R1 plus R2, and then 1 over Req equals 1 over R1 plus 1 over R2. Okay, I know this was a lot of information, so don't worry, we'll have time once I get back on either Tuesday or Wednesday when you see me, and I'll review this and work through a couple other problems with y'all. So try the homework. Answers are posted up online. Get through what you can. And again, we'll work through this and review all of this before we start our combo circuits.